This video is on different sorting algorithms. So the need for sorting comes directly from the last video that we talked about with searching. The binary search is an optimal algorithm, which means it's as fast as it can be theoretically. Okay, so there are physical limits or logical limits to how fast an algorithm can be. So binary search is the best there is. So you want to use it whenever you can, but it requires the data, underlying data, to be sorted. So that's the issue. So if you can, it's best to keep things sorted as you go. If you think back to the ordered linked list that we did, it basically always inserted data in the right spot as it was going along. And that's usually a better strategy than trying to sort pre-existing data. But the fact remains, in the real world, we often get data dumped on us that we did not necessarily collect ourselves. So this data has to be sorted if we're going to be able to use a binary search on it. Okay. So sorting is important, can be very time consuming. So a lot of work has been done on this. So computer scientists are always trying to find a faster way to sort. So the faster way here, there are a couple of dimensions that we'll talk about as we go through. The first is just the performance and time. So the time that it takes to do a certain sort. That's an important dynamic. Another dynamic though is how much extra memory gets taken up by the search algorithm. Some of them require a lot, some of them don't require as much. So in some situations that can be a factor. I think the overall thing to say before we get started on the specifics is that the perfect sort algorithm for any given set of data can't really be known until you run them all against the data. There are always slight variations, if it's in reverse sorted order, if it's mostly sorted, if the variances are a lot between them, all of those can affect which particular sorting algorithm works the best. So all you can do is find one that in general meets the requirements that you're looking for. Okay. So as far as the theoretical limits, again, in keeping with what we've done before, we're going to kind of brush over the math involved in these calculations. But know that in algorithms class, which is probably the next class that you take, you'll get more into that. But for sorting, the theoretical limit is n log n. So that's n times the binary log of n is the best we can get. So when we're looking at the numbers, that's kind of the best case scenario. Okay, so that's slower than n would be, or log n. Log n's the fastest one we talk about. So it goes from log n to n log n to n squared. Okay, so that's kind of the range with the log n being the best. So the first sort that they talk about in the book is bubble sort. And bubble sort, partly because it has a funny name, partly because it's super not efficient, has a bad reputation. So we talk about it in class, but it's not something you would ever really do. I think that would be a bad idea. Um, so it is a place to start. Okay, it's simple to describe. I think that's the main issue. So the idea of a bubble sort and why it's called a bubble sort is that you start by comparing the first two elements and swap them if the first one is bigger. So you do that all the way through your list. So at the end, the biggest item or the biggest element is all the way to the right in its proper position. Okay. The rest of it, you can't tell anything at all about. Okay. So I've got an example here. We've got 6, 21, 15, 4, 18, and 2. So we're going to start by comparing the first two here, the 6 and the 21. They're in the correct order, so we don't do anything. Okay. The next one, and this is all for the first pass, by the way. Next, we're going to compare the 21 with a 15. Okay. And I've already done the switch here, so we've swapped those. Okay. We then compare the 21 to the 4 and swap those. We compare the 21 to the 18 and swap those. And finally compare the 21, sorry, to the 2 and swap those. Okay. So after all of that, all we can say is that this particular element, the one over here, is now sorted. We know that it is in the right spot. Okay. The others clearly are not in the right spot. Okay. So with our, what is this? 1, 2, 3, 4, 5, 6 elements that we have, we did 5 comparisons and 4 swaps, but now we have that one in the correct place. Okay. Here's the code to implement this. It's not too bad. We're going to make this templated. We're going to send along an array and the length. Okay. We've got 2 loops here. So 2 iterators. That's because we're going to do one less every time as we go through. And then we go through, we're just, again, checking. So this is a loop that checks every single element against its neighbor. This is the one that starts that process at a different level each time. Okay. And then here's just the swapping that we're doing if this is the case. Okay. If the element is bigger than the one next to it, then it's going to do this swap. Okay. So when you're looking at its big O, this is a big O of n squared. We can almost guess that pretty easily. There are 2 loops here that go kind of through the whole thing. So there's n here and n here. So for every n, you do it n times, that's n squared. Okay. And that was a really rough estimate. This also has a lot of swaps, so a lot of memory usage, a lot of machinations back and forth, okay, which makes it not a great sort at all. Okay. So the next sort we're going to talk about is the selection sort. It has the same efficiency class. It's still an n squared, as does bubble sort, but this is going to accomplish that without moving the elements around so much. So it makes it a better choice. In fact, selection sort is not the worst thing to use if you know you're going to have a small amount of data that doesn't need to be sorted very often, and performance is not a big issue. Okay. So you won't be laughed at quite so much if you pull out a selection sort, especially, I mean, it gets the job done. It's simpler code. So especially if it's a small, quick and dirty data set you need to sort, nothing wrong with pulling out the selection sort. Okay. So it's a little more complicated to code, and we'll see that the more efficient an algorithm is, typically the more complicated it is to code. Okay. We've templated this one as well, but we're going to have 2 functions here. So we need some helper functions that are going to find the minimum location. Oh, let me talk about the algorithm first. Get ahead of myself. So the idea of a selection sort is that you're going to find the index that contains the smallest element. You're going to move that element to the beginning of the list. Okay, and then do that again as you go through. So we're still going to have the n squared, still going to have the 2 things. But rather than swapping all the time, we're going to look through. We're going to do what I like to call the king of the hill algorithm. And you're going to find the smallest element that's left. You're going to capture its index, and you're going to swap that index with the smallest position first, and then the second smallest, and so forth. Okay. So here's what the code's going to look like. Again, we're going to need a function to find that minimum location. We're going to need a function to do the swap. Okay. So let's start with the selection sort itself. Okay. So it's going to take a list. It's going to take the length as always. It's going to go through here. Okay. For the location from 0 to the length, it's going to go through every cell. It's going to calculate the min index, calling this min location function with a list, the location, okay, that we're iterating through here, and the length -1. It's then going to swap list and location, okay, with that minimum index, okay. So those are the functions it's going to call. It first calls the min location function, which is up here, okay. This is where the n squared comes from. We're going through every element in the main function and every element again up here. Okay, so we're sending along this first and last so we can change where we are moving through the array. Okay, and we're going to go through our list here and see which one's smallest, and we're going to keep that index there, and we're going to return the index that was the smallest. Okay, so once we've done that in selection sort, we're then going to call a swap. The swap function here, it's going to use a temp to basically switch between the first and the second locations. Okay. That's all that does. Okay. So there's another sort that's also at the big O of n squared that we talk about, and that's the insertion sort. So the insertion sort, I think the reason we talk about it's not a great sort. Okay. So it's a lot of overhead. So it's a lot of swapping around, kind of like bubble sort. But it has some techniques that led to the development of the faster algorithm. So we can talk about it. So the idea behind the insertion sort then is you're going to build your sorted list one element at a time. So when you start that you're sorted. So your list is say 10 elements. You assume that the sorted list is only the first element. One element cannot be out of order. There's only one element. Okay. Then as we add elements one at a time, so we go to add the second element of our list, we'll put it either to the right or the left of that element, of that first element. When we add the third, we'll put it in position. The fourth, put it in position, and so forth. Okay. The efficiency issue comes in that if you have searched through 9 of your elements in your 10 element array, and you have those all sorted, and life is good, and the 10th element is the smallest. Okay, then you have to swap out that 10th element with the first element, but you also, to do that, you have to move every element, first to second, second to third, third to fourth, fourth to fifth, fifth to sixth, sixth to seventh, seventh to eighth, and eighth to ninth, and ninth to 10th. Okay, that's the overhead that we talk about. Okay, but the idea that we're going to have a sorted and unsorted portion of the list that we're working on is what we're going to utilize with the other algorithms that we talk about. Okay. So again, we've said that the best time that we can have, or the best efficiency class, is n log n. Okay. And Quicksort on average does that. So that's a good thing. Okay. The worrying part is that in the worst case, so if we have absolutely the worst numbers that head its way, it's going to be an n squared, which is just like insert sort and selection sort and bubble sort. Okay. So we have to be cautious in using this. We'll talk about when and where we use it. Okay. So the basic way this works, you have your array, you're going to pick a pivot point. Okay. The pivot point can either be the first element, it can be the element that's in the middle, if we know how long the elements are. It can be an average of the element. There are all kinds of ways that we can do this. It could be based on knowledge of where the data tends to be. Okay. So you pick this pivot point, okay, and you move it to the front, and then you're going to go through and you're going to divide the remaining elements. We're going to do what's called a semi-sort. We're going to divide the remaining elements into those that are less than the pivot and those that are greater than the pivot. Okay. Well, then keep track of where that line is. And then when we swap out the last of the items smaller than the pivot with the pivot, we're going to have a semi-sorted list. Okay. So that's kind of the idea. That gets you partway through. You then have to quick sort each sub list as you go along. And then finally you put them all back together. Okay. So the more formal way to look at this, we're going to say if the list size is greater than 1. Again, if it's 1, you're done. You can't sort a list of 1. It's already sorted. Okay. You're going to partition the list into 2 subsets. We could call that lower sublist and upper sublist. Again, that uses the pivot. So the lower sublist is those are all elements that are lower or smaller than the pivot. The upper sublist are those that are greater than the pivot. They're in no order themselves, except the one group is all smaller, the other group is all bigger. Okay. We're going to then quick sort each of those 2 halves, which involves breaking them up further. Okay. Until we get down to only 1. Okay. And then we're going to combine those back together. So here's an example which I think will make things a little bit clearer. Okay. So we have this example here with 9 elements, random data here. So in this is the example from the book that I've coded up differently myself. In this one, we have 8 is the biggest index. So we're just going to assume that maybe 4 is the one that we're going to take for the pivot. Okay. That has no meaning. It's not in the middle for any reason except randomness, but that's what we're going to do. You got to pick something. So we're going to say that 50 is our pivot. So we go ahead and put 50 over here, and I've marked that in green. Okay. So we also have to keep track of the last element that is smaller than the pivot in our partition data. Okay. So that starts off being 0. So we're now going to look at this first element 82. 82 is bigger than 50, so we don't need to swap anything. It's okay where it's at. Okay. And we're going to keep our swap point at 0. Okay. We're now going to look at the next element, 50. So in this case, okay, so we're looking here at the 25 and 82. Okay. The 25 is bigger. Sorry, the 25 is smaller than the 82. So we have to swap those. Okay. So now we have the 25 here. It's a light blue, meaning it's less than 50. And we have the 82, meaning that it is greater than 50. Again, and I said that incorrectly. I'm comparing the 25 to the 50, not to the 82. Okay. Because 25 is less than 50, it goes here, and we increase our swap pivot to be a 1. Okay. At this point, here's our pivot in green. The light blue is the items that are partitioned to be less than the pivot. And the dark blue are those that are greater than the pivot. Okay. Now, if we keep doing that, we look at the 94, it's going to stay to the right. The 45 is less than 50. It's going to go over here. The 60 is greater than 50. It stays to the right. The 78, greater than 50, stays to the right. The 32 is going to get sent over to the side of less than the pivot. 92 is greater. So when we're done with all of those steps, we have our pivot. We have the elements that are less than the pivot in no particular order. We have the elements that are greater than the pivot in no particular order. And we have that our swap pivot points to 3, which is the last of the elements that are smaller than the pivot. Okay. We can now swap those two, swap the 50 with the 32. We've now divided up our list into our lower sublist, which contains all the elements that are less than our pivot of 50. And then to the right, all the elements that are greater than our pivot. Okay. And 50 is now sorted, right? 50 is not going to move. It's in the correct position. Okay. We then have to go back and do a quick sort on this part and a quick sort on that part. Now, what happens in this quick sort often is that once you get down to a small enough set size, it will switch to a selection sort just because there's less overhead. So in this case, we would probably use a selection sort, certainly on the left one, maybe on both of these. Okay. Which is just a way to make that more efficient. Okay. So the book has all the code for implementing the quick sort and all the different functions that it needs. It's going to need a function to partition the list. It's going to need a function to swap elements. And then there's both a recursive function and a regular quick sort function. It's recursive because it keeps calling itself, but it has to have a function to call and start the recursion. So there are two functions there. So you can look through that for sure. Okay. But the real issue with this is finding ways to pick the pivot correctly. You want your pivot ideally to divide your set in half. If it doesn't, if it only divides it into really unequal halves, then the efficiency is going to go way down. Okay. So the last sort we're going to cover is the merge sort. Okay. The merge sort is always at n log n. Okay. No matter what. So it has the best performance. So why don't we use it all the time? The issue is one of memory usage. And we're gonna see how that's an issue. I've got a diagram here from the book. So the memory usage is so high, even though it's fast, that we typically are going to use it only with things that are memory efficient, like linked lists. Okay. With a linked list, you're just moving pointers around, you're not actually moving data, so it's going to work okay. So just like the quick sort was, merge sort's going to be a recursive algorithm. I didn't say it with quicksort, but they both use a divide and conquer, which we'll talk about in algorithms class, to basically split up the problem into sub problems, and then solve those sub problems, then combine to get your answer. Okay, so that's the basic idea. But what merge sort does, it divides the set in half. It does no comparisons to do that. There's no guarantee as to what is on each side. As far as there's no pivot, there's no anything. You just cut it in half. Okay. You then sort each half. You then cut it in half again, sort each half. You keep going till you only have one element. When you have that one element, you then start combining it back and building your new list based on the values that are in those single elements. Okay. So again, the general algorithm looks like if the list is of a size greater than one, we're going to divide the list into two sublists, merge sort the first, merge sort the second, and then merge those two back together. Okay. So here's a way as a visual on how it looks. So if we have this 35, 28, 18, 45, 62, 48, 30, 38, we're going to divide it just by the size and the number of elements. Okay, so we're not looking at anything at all um, in terms of what's there. So this is the first four, this is the last four. That's it. Okay, we're not equal to one. We're going to subdivide it again. Okay, into four groups here. Okay, that's not equal to one yet. We divide it up. So now we have these 8 sets. One set just of 38 or 35, 28, and so forth. Okay. We now start to merge these back together. We merge them for this set by looking at of the two that are here, which is the smallest, 28, mark it off, then 35. We merge these together. The 18's first, 45 is second. On this one, the 48, then the 62. On this one, the 30, then the 38. Okay. We're now going to merge those two smaller groups together. So again, of these four elements, we pick the smallest first, which is the 18. Notice that we only have to look at the head of these two lists. Okay. So we look at 18 versus 28. The 18 goes there. So now we have a 45 here. We look at the 25 and the 45. The 28 goes there. We have the 35 and the 45. The 35 goes there, which leaves a 45. Same thing over here. The 30 is the smallest in this group, the 38, the 48, the 62. We then merge it all back together by looking at the smallest in this sublist and the smallest in this sublist. So the 18 goes there. The new smallest here is 28. 28 is still smaller than 30. It goes next. Then the 30 goes, then the 35, then the 38, then the 45. And at this point, once we've chosen the 45 here, we can just move over the 48 and the 62 because there's nothing to compare it to over here. Okay. So again, the code for all that is in the book. Okay. So the question always becomes, how do we select a sort algorithm? And again, there's no way, unless you know exactly what it is, how it's going to work. So we just go some general guidelines. Okay. So again, the ones that I would memorize and the ones that I would know and be able to use in case anybody asks. First off, is a selection sort. Again, it's a quick and dirty, not quick, it's quick to code, simple to code. Okay. And if it's a small data set or it's not going to be used very often or performance is not an issue, you can use it. Okay. So quick sort, it has the best average efficiency, but has a worst case scenario than the merge sort. But it also requires a lot less memory. So if there's one sort you're going to use most of the time, quick sort is going to be the way to go. Okay, it's the most generally useful sort that we can have. Okay, again, if you're using it, you want to make sure you find a way to pick that pivot in a method that works with your data. Okay, as you get data as you go along, it'll make more sense how you can pick that pivot point more accurately. Okay. And then finally, we have merge sort, which is the best performance in all cases for sure, but it can go through a lot of memory. So if memory is a concern at all, you wouldn't want to use it. Um, in fact, the only time it's definitely what you use if you're using it, if your data is stored in a memory efficient data structure, such as a linked list or a tree or something else. So that's the basic idea. Okay. So that's sorting. Sorting is something we do a lot. Okay. And it's certainly worth getting the sort correct.